Hello, everyone. My name is Ameya Velingker, and I'm a research scientist at Google Research. And today I will be speaking about linear space streaming lower bounds for approximating CSPs. This is based on joint work with my amazing set of collaborators, Chi-Ning, Sasha, Madhu, and Santhoshini. So just to give you an overview of the talk, I'll start by introducing max CSPs and the streaming model in which we operate, delving into some prior work and history of the problem. This will segue nicely into our results and main contributions of the talk. And then I'll spend some of the remaining time giving you a flavor of the techniques that are used in our proofs. And this will be followed by a conclusion, of course. So let's dive right in. So the main problem we're trying to solve in this talk are max constraint satisfaction problems, or CSPs. So in the setup, we're given n variables coming from a domain of size q, as well as a set of predicates. This is basically a family of allowed functions. So each function f takes in k arguments and outputs either 0 or 1. And I'm allowed to use a number of different functions, so this forms my family. And I'm also given constraints C1 through Cm, each of which is ideally satisfied. So each constraint consists of a function from my function family, as well as a set of k variables. And we say that the constraint is satisfied if the function applied to my k chosen variables equals 1. And the task is to simply maximize over all possible assignments of the variables the value or number of satisfied constraints. So it turns out the max CSP formulation covers a lot of interesting problems that have been of interest to theorists over the years. But let's first look at the example of the celebrated max cut problem, in which we are given a graph and asked to assign all the nodes into one of two partitions so as to maximize the number of edges crossing the partitions. Okay, so in this particular example, I have a graph on 7 nodes, and I've partitioned the nodes so as to produce a cut size of 6. Now, it turns out this is not actually the max cut you can achieve. It's possible to do better by partitioning the nodes into a more clever set of partitions. To show you that this falls under the max CSP framework that I discussed on the previous slide, we can assign variables to each of the nodes, taking value 0 or 1. This basically indicates which partition I've assigned each node to. And then my predicates are quite simple. I only have one type of function, which is the exclusive OR function on two variables. And it's easy to see that this gives rise to constraints that tell us whether each edge crosses the bipartition or not. This is basically because uh, the output of the exclusive OR function is 1 if and only if the arguments are distinct. Now let's talk a bit about the streaming model. So in this setup, my algorithm actually has access to constraints arriving as a data stream. So it's allowed to process each constraint one after another. And the caveat is, of course, that it is only allotted a limited amount of memory. Typically, we require this to be sublinear in n, the number of variables. And the task is to output an approximation to the max CSP value. So this is a value that's bounded by the max CSP value from above and alpha times this value from below. So to illustrate what's going on, here's my streaming algorithm initialized with a state S0, which again has to lie in my allotted memory. And then I'm given a set of constraints as a data stream. So my algorithm will first process C1, and it will update its state to S1. Then it will do processing of C2, updating its state to S2. And similarly, it will continue processing every single remaining constraint in order. Finally, it will output this state SM, from which it will compute a value to output. So let's talk a bit about the prior work here. So it's rather fitting that STOC is taking place in Italy this year, because in fact our story begins in Italy just over 10 years ago. Turns out there was this workshop in the town of Bertinoro back in 2011, where it was asked whether there exists a streaming algorithm for maxcut that achieves an approximation ratio better than 1/2 using sublinear space. Okay, and you can ask this question more generally for other max CSPs as well. So let me just give you an idea for why 1/2 and the sublinear space threshold are the right thresholds to consider. And this essentially arises from the existence of what I call two basic algorithms for maxcut. So on the one hand, there's this algorithm that uses logarithmic space, and it works using the following observation that if we just choose a random partition of the nodes, this will have a cut that has, on expectation, 1/2 times the total number of edges. Okay, and in particular, there exists some cut with at least that many edges. So this suggests a very simple algorithm where we can just store a counter and count the total number of edges as they come in and output half that value. Okay, so this gives us a 1/2 approximation. On the other hand, there's this other algorithm which gives an approximation of any desired quality. So we can get 1 minus epsilon for any epsilon bigger than 0. And this operates via building what is known as a cut sparsifier. Okay, so it turns out this uses roughly linear space up to some polylog factors. And the question is essentially whether one can interpolate between algorithms 1 and 2. So there's been some prior work on investigating this for maxcut. And this line of work begins with the work of Kaprilov, Khanna, and Madhu. And essentially what they show is that to do better than a 1/2 approximation ratio, you need square root of n space. This now leaves open the question of whether one can do better than 1/2 with more than square root of n space. And this was in fact the motivation for my subsequent work with the same set of authors, in which we actually upgraded this space lower bound to a linear space bound. The caveat is, of course, that we didn't quite handle all approximation ratios beyond 1/2. But this was soon rectified by the fascinating work of Kaprilov and Krachun, where they showed that basically you need linear space to do anything better than 1/2. So in a sense, this final result was not that surprising. Turns out streaming algorithms are quite limited in memory, and that sort of precludes a lot of natural approaches to solving maxcut. But there was still this sort of question, is the streaming model good for anything in the CSP world? That is, are there any classes of max CSPs for which you can do better than the so-called trivial approximation, or basically outputting some constant fraction of the total number of constraints? So it turns out in my work with Santhoshini as well as Velusamy, we showed that for the max 2 and problem, you can actually get an approximation ratio that's better than the trivial 1/4. And this can be done via a polylog n space algorithm. This was subsequently improved in a work of Chou, Golovnev, and Velusamy, where they basically pinned down the optimal approximation ratio. And moreover, they actually pinned down the approximation ratio for all Boolean max 2 CSP problems. And they get polylog n space algorithms. And then finally, there was this work that looked at approximability of max k-end, for which they proved some non-trivial approximation ratios. What about space lower bounds? So turns out that somehow square root of n is a natural space bound that comes up in a lot of these works. So for instance, the Boolean max 2 CSP paper that I was referring to in the previous slide, they also prove square root of n space lower bounds for going beyond the natural approximation threshold. There are also some works that show square root of n bounds for what are called one-wise independent families, as well as linear threshold functions. But what I want to stress is that somehow square root of n bounds really do come naturally in the streaming setting for max CSP. And somehow it turns out to be quite difficult to upgrade square root of n bounds to linear space bounds. In fact, the only major work we really knew prior to this was Kapralov-Krachun, where they showed the linear space bound for max cut. And what our work did was to essentially show linear space bounds for a wider class of max CSPs. So having said that, let's delve into the details of our results. So again, the problem is to figure out which max CSPs can be approximated beyond the trivial approximation using sublinear space. Or conversely, can we prove linear space lower bounds for max CSPs? And what we're able to show is that there turns out to be some natural class of CSPs, which we call wide families, for which you can actually show a linear space lower bound. Okay, so I'll talk more about what a wide family is, but for now I'll just say that there's a lot of max CSPs that fall under this class. For instance, max KSAT, Q colorability, etc. And the other result we show is that we essentially establish an upper bound on the optimal approximation ratio for all max CSP families. Okay, just a word about the techniques. We essentially extend the machinery of Kapralov and Krachun, and we upgrade some of the Fourier analytic techniques to analyze a wider range of communication problems, which allow us to get linear space lower bounds for a wider range of CSPs. Okay, so now let me talk a bit about what families of CSPs our result applies to. So for this, I need to first introduce this notion of one-wise independence. So it turns out that if we have a distribution over k-tuples, we say that it is one-wise independent if its marginals on all the coordinates are uniform. And then we can say that a family of functions supports one-wise independence if for each function in the family there is a one-wise independent distribution supported on its satisfying assignments. Okay, so for the example of max cut, remember that the relevant function is the XOR function on two variables. Turns out we can just choose this one-wise independent distribution D, which is uniform over 0, 1, and 1, 0. These are the satisfying assignments of XOR. So indeed, this is one-wise independent. Alternatively, we have this notion of wide families. Okay, so for this, we need to define something called the width, which basically does the following. So for a given function, we can look at a single k-tuple or point, and the width here is essentially the fraction of satisfying assignments of f that lie on this line through the point. Okay, so this line consists of various translations and shifts of my point A. And the width of the function is essentially the max over all possible lines. Okay, and we say that a family of functions is wide if all of its functions have this maximal width of 1. That is, there's some line such that all points on it are satisfying for f. Now, it turns out that in the max cut world, this is also a wide family. Okay, and this is simply because the satisfying assignments of my XOR function all lie on a single line. Indeed, it turns out that all wide families are also one-wise independent, but the converse is not true. So for instance, I can take this example of XOR on 3 variables. Turns out this is one-wise independent, but it is not actually wide. So a previous result due to my co-authors showed that if you have a one-wise independent family, you can always show a square root of n space lower bound. And what we essentially do is to upgrade this lower bound to a linear space lower bound. But the caveat is that instead of operating on all one-wise independent families, we handle wide CSP families. But this still captures a lot of the interesting max CSPs that people consider, as I mentioned in the previous slide. Okay, so in the remaining time, I will give some overview of the techniques we use and how the lower bound proof goes. So as is customary in a lot of streaming lower bounds, we actually analyze a multi-party communication game and reduce it to the max CSP. So um, in essence, we can prove a lower bound on the communication complexity of a multi-party communication game. And the particular game we consider is something we call the implicit randomized mask detection problem. So this is a one-shot sequential game involving T players. Okay, so the idea is that each player processes his input and passes a message to the next player, and then this keeps going on until the final player outputs an answer. So let's talk about the structure of this game. So it turns out there's this implicit or um, hidden variable vector, which we call x star. So in this particular example, we have n equal to 10 hidden variables, and each one is from a domain size of q equals 3. Turns out that our instance comes from either a yes distribution or a no distribution um, over k tuples. Okay, and the problem is essentially for the players to distinguish which of these distributions the game came from. Okay, so now let's talk a bit about the input that each player receives. So each player, player T receives a matrix AT as well as a vector Z sub T. So let me describe what this matrix is. So it turns out the matrix consists of several blocks, and each block is a k by n matrix. So each column corresponds to a hidden variable. And the structure is that each row is one sparse. Okay, so there are exactly k columns that have a non-zero value, and these correspond to k hidden variables. Okay, so in this particular example, columns 2, 4, and 7 are non-zero, so this somehow corresponds to x sub 2, x sub 4, and x sub 7. Okay, now I have a second block in this example, and this corresponds to another set of 3 variables. I'm also given this vector z sub t, which is produced by doing a matrix vector product, and then adding this additive term, which is sampled from one of these 2 yes or no distributions. Okay, and then the task, I remind you, is to output yes or no. This will be done by the final player. Okay, so now let me talk about the reduction to the streaming CSP and how we produce a streaming CSP instance. Essentially what happens is that we can use player T's matrix and vector to generate CSP constraints in the natural way. So each block of the matrix AT corresponds to k hidden variables. So we can generate some kind of natural CSP constraint over these k hidden variables. And basically we can do this for each block. So it will give some set of constraints. And then I can view these constraints as one chunk of a data stream. Okay, so this will give me a CSP instance. Okay, so it turns out we have one slight problem, which is that we don't quite know how to directly prove the hardness of this communication game. So what we do is instead prove a linear communication lower bound for a folded version of this game, which we call the implicit folded randomized mask detection problem. So let me describe the conversion here. So let me remind you the inputs that player T received, this matrix AT and vector ZT. And what we do is for each block in AT, we pick a certain column that is non-zero. So for block 1 here, we've chosen the 4th column, and we've chosen the 9th column for the second block. And what we do is basically collapse each block by removing the row corresponding to the non-zero entry in the column. and then replace all other entries in the column with a -1. Okay, so this is how it works for this example. And instead of zt, we actually look at this vector wt, which is simply a matrix vector product, or it can be a uniform vector. And with some work, we can show that the folded version of this problem is actually no harder than the unfolded version, which in turn is upper bounded by the hardness of the CSP problem. Okay, so the technical contribution is mainly to prove a linear communication lower bound for this folded communication problem. Okay, so how do we do this? So first of all, by Yao's principle, we can assume that the protocol we analyze is a deterministic protocol. And the idea is that each player through the course of the game has a certain posterior distribution for this hidden vector x star. Okay, so it turns out that this posterior distribution is actually nice in structure. It is a uniform distribution over some set. And let's take a look at our communication. So in this diagram, player I sends message SI to player I+1 after processing his own input. And let's take a look at how the posterior distributions behave. So player 1 starts out with a posterior distribution of x star, which is uniform over the set B1. Now, what player 2 does is takes B1 and tries to update this posterior set. So in particular, player 2 has received a message S1 from player 1. And what this does is kind of correspond to certain possible x star from which S1 could have arisen. So this gives rise to a set B2. And basically, player 2 knows that x star lies in both B1 and B2, so we can update this posterior set to the intersection of these two sets. And then similarly, player 3, using the communication he receives, can update his posterior set to some intersection. And this will continue onwards until player T has his own posterior distribution over a much smaller set. So again, the posterior sets are easy to characterize. They're given by successive intersections. And they basically capture the ability to distinguish the yes distribution from the no distribution. Okay, so the goal is to show that if the players actually communicate a sublinear number of bits, then they cannot distinguish the yes case from the no case. And how do we do this? So the first step is to show that it actually suffices to analyze these posterior distributions I mentioned. And this is due to some kind of data processing inequality, which allows us to upper bound a relevant quantity by a certain total variation distance. And then step 2 is to basically show that this total variation distance upper bound can come from some Fourier properties of the posterior set. So here, B is the posterior set, and we can look at this fancy sum involving the Fourier weights of the indicator function on this set B. Okay, and we need to show that it actually decays in an appropriate manner. And turns out if this is the case, we get the relevant TVD bound. And then the final step is to inductively show that these Fourier properties hold with high probability. So this will be achieved by mapping to some combinatorial problems and using a delicate counting argument. Okay, so just to conclude the talk, we managed to actually prove linear space streaming lower bounds for a large class of max CSP problems. So this is essentially extending the result of Kapralov and Krachun, and we also extend the Fourier machinery for this purpose. I think a future direction would be to investigate whether the linear space streaming bound can hold for a more general class of CSPs beyond just our wide families. Okay, and that's it for this talk. Thank you for listening.